Okay, so good morning, everybody. Welcome to the day 2, session 1. This is the third lecture on adjacency matrices on graphs. Okay, so yesterday, towards the end of the second lecture, so we were discussing about Ferrand-Robinier's theorem for graphs. Okay, for the graph version. Okay, so that says that if G is a connected graph with adjacency matrix A of G A, okay, and if the eigenvalues are arranged in this way, lambda 1 greater than or equal to lambda 2 greater than or equal to lambda n, okay, with the corresponding eigenvectors x1 to xn, okay, then we can conclude these things. The largest eigenvalue should be always greater than or equal to negative of the smallest eigenvalue, okay. In other words, if you know the notion of spectral radius, so this says that spectral radius is an eigenvalue. So this need not be true for arbitrary matrices. And then the largest eigenvalue lambda 1, okay, this should be simple. That means the second largest eigenvalue should be strictly less than the largest eigenvalue. Okay, multiplicity is equal to 1 for lambda 1. Okay, and the eigenvector corresponding to the eigenvalue lambda 1 should be positive. Okay, there exists a so that eigenvector is positive. Okay. In fact, for the connected graph, if you take any other eigenvector corresponding to lambda 1, that will have a positive entries. Okay. Yeah, up to sign. Okay. Either everything can be negative or everything can be positive. And so this result we have seen. So today I have properly stated this result. So G is a graph. Then G is bipartite if and only if the following holds. Okay. So whenever lambda is an eigenvalue of A of G, minus lambda is also an eigenvalue of A of G. Okay. For the one side of the proof, if G is bipartite, then just we use the block matrix property. Okay, something like that. So for the bipartite graph, our adjacency matrix looks like this. Okay, so you're using just manipulating the eigen equation, you can get whenever lambda is an eigenvalue of G, minus lambda is also an eigenvalue of G. Okay, so that is the one side of the proof. And for the converse, what we did, just we have seen the spectral moments, that is lambda 1 power k up to lambda n power k. This counts the number of closed walks. Okay, number of closed walks of length k. Okay, since k, if k is an odd number, if the matrix has this property, lambda is an eigenvalue, implies minus lambda is also an eigenvalue, then this property implies that this sum is equal to 0 whenever k is odd. That means the number of closed walks of odd length is equal to 0. In particular, number of closed paths, that is the cycles, number of odd cycles is equal to 0. That is same as saying that the graph G is bipartite. Okay. Now, today we will see an interesting extension of this result. So, a much more general version. This says that if you assume your graph is connected, okay, and when this lambda 1 is equal to minus lambda n, that is the largest eigenvalue is equal to the negative of the smallest eigenvalue, then the graph is bipartite. Okay, so this is the hypothesis is little weaker than the previous statement. So there we are asking for every eigenvalue, whenever lambda is an eigenvalue, minus lambda is also eigenvalue. We are asking here only the largest eigenvalue and the negative of the largest eigenvalue. Both of them are eigenvalues. Okay. Our largest eigenvalue is equal to negative of the smallest eigenvalue. If this is true, then we claim this is G is a bipartite graph. Okay, so let us start with the proof. So let us take the eigen equation AY equal to lambda n into AX is equal to lambda n into x. Okay, so with x is different from 0. So what is the assumption? Assumption is lambda 1 is equal to minus lambda n. Okay, lambda 1 is equal to, the claim is G is bipartite. So now let us see that this quantity x transpose. Okay, so note that so x is an eigenvector corresponding to lambda n. So x will have both positive and negative entries. So now let us define a vector, new vector y, in this way. Okay, absolute value of x. So by this notation, I mean take the absolute values of entries of this vector x. Okay. Now, lambda n is equal to, okay, maybe I can normalize this. You take x transpose x to have equal to 1. Okay. So with this assumption, I'm going to get lambda n is equal to x transpose ax. Okay. What I'm doing, just simply pre-multiply by or take the dot product of the vector x with this equation. So in the left hand side, I will get x transpose ax that I'm writing here, and in the other side you have lambda n into x transpose x, that is just lambda n. Okay, just apply the definition. What are you going to get? So this is same as summation aij xi into xj. Okay, this is double summation ij. Okay, so hence this implies absolute value of lambda n is less than or equal to summation ij absolute value of aij into absolute value of xi into absolute value of xj. Okay, just from here to here, I'm just applying triangle inequality. Okay, take absolute value, this equality will become inequality because of the triangle inequality. Okay, and this is same as you see summation ij. Aij is either 0 or 1, so I don't need any this thing absolute value, and absolute value of xi into yi, if you see, that is by the definition of y, this is our yi into yj. Okay, now just include one more slide. And what about this quantity? This is same as y transpose ay. Okay, and this is less than or equal to lambda 1. Okay, can anyone of you justify the last inequality? From here to here, how to do? Okay, let us see. See, x transpose x is equal to 1. So that will imply y transpose y is also equal to 1. You agree? Okay. And the adjacency matrix is symmetric matrix. So then what is the formula for the largest eigenvalue? Yesterday we have seen, right? Lambda 1 is nothing but maximum over y different from 0, y transpose ay, maybe y I'm already using here. Let us take z. Z not equal to 0, z transpose az divided by z transpose z. So this is greater than or equal to, for a particular vector, I am taking this y transpose ay divided by y transpose y, that is equal to 1. Okay. So since I have this, so I can write this inequality here. Okay. But what is the hypothesis? Lambda 1 is equal to minus lambda n. Okay. Lambda 1 equal to minus lambda n. Hence, these all the inequalities will become equality. Okay. After taking absolute value, minus lambda n is just lambda 1. Okay. So everywhere it will become equality. So therefore, all the, okay, since lambda 1 is equal to minus lambda n, therefore all the inequalities in the above are indeed equalities. Okay. So that means that lambda 1 is equal to y transpose ay. I think one of you yesterday asked in the variational characterization when I gave. Suppose for a vector y, if the maximum is attained or if the minimum is attained, whether that is going to imply whether that is an eigenvector or not. Okay, indeed that is true. Okay, so here this is going to tell me ay is equal to lambda y. Okay, lambda 1 into y. Just a minute. Okay. Now, there's another interesting property of non-negative matrices. So we have seen, right? Lambda 1 is the largest eigenvalue. It has multiplicity, algebraic multiplicity equal to 1, and it has a positive eigenvector. Okay. So since it's a symmetric matrix, algebraic multiplicity, geometric multiplicity, everything is the same. Okay. So y is an eigenvector corresponding to the eigenvalue lambda 1. Okay. So y should be either strictly positive or strictly negative, but y, we by the definition we have taken y to be absolute value of xi. So yi is every entry of yi is strictly greater than 0. So this implies every entry of x that is different from 0. Okay, for every I. Okay, so let me just recall what are we doing. So our assumption is lambda 1 is equal to minus lambda n. Okay, so take the eigenvector corresponding to lambda n, that is x. Okay, using that vector x, construct a vector y. Okay, so for this vector y, okay, we are able to show that the vector y is indeed an eigenvector corresponding to the eigenvalue lambda 1. Okay, that shows that all the entries of y are different from 0. So that forces that all the entries of xi are different from 0. Okay, note that the connectedness we have used crucially here. So in this step, since the graph is connected, so we are able to use this. Since G is connected, if G is not connected, then this step I can't do. Okay, so now xi is different from 0 for every I. Okay, and also note that the summation aij xi xj, this is equal to summation absolute value of aij into absolute value of xi into absolute value of xi. When the equality will hold here, so we are having in the triangle inequality, okay, we have equality here. Okay, so that forces that all these products, okay, all the products xi into xj, okay, corresponding to the edges, okay, I adjacent to j, okay, corresponding to the edges have the same sign. Okay, only when all of them are having same positive or negative sign, then only I will get a equality over here in this place. Okay, in this line I will get a equality only when xi and xj, whenever there is an edge between I and j, the product xi and xj should have same sign. Okay, now note that lambda n is nothing but x transpose ax, which is strictly less than 0. Okay, so what are you saying? Like xi into xj, every product should have same sign. Okay, so now on top of it I have this lambda n is equal to x transpose axi. Okay, so that means that the variational characterization for lambda n, if you use that, I'm getting the minimum over this x transpose ax divided by x transpose x. Okay, so the minimum is less than or equal to 0. So each xi into xj should be strictly less than 0 whenever I is adjacent to j. Okay, so the equality in the triangle inequality tells me both of them should have this the products xi xj should have always the same sign. Okay, but I don't know whether it is positive or not. But if you use the fact that lambda n is equal to x transpose ax and lambda n is strictly less than 0, okay, And applying this variational characterization, we are going to get xi into xj is strictly less than 0. Okay. So in terms of vertices, what does it say? Whenever you have an edge, if you look at the end points of the or end vertices of the edge, if one end vertex has a positive sign, the other end vertex should have a negative sign corresponding to the vector x. Okay. So x is x1, x2 up to xn. This is this thing you can assign to the vertices. Okay. So if there is an edge from I to j, okay, then xi into xj, the components corresponding to I and jth vertex, ith and jth vertex, okay, xi and xj, if you take the product should be strictly less than 0. Okay, that means that one vertex should be xi should be positive and xj should be negative, or xi should be negative, xj should be positive. Okay, so now this gives us a clear bipartition. You take v1 to be set of all I such that xi is strictly less than 0, and you take v2 to be set of all I such that xi is strictly greater than 0. Is it a bipartition? Is it a bipartition? What do you have to check? Any one of you may unmute yourself and you can say why it is a bipartition. You can hear me, right?
Yes, sir.
Okay. So what do you have to check, whether it's a bipartition or not? So first of all, whether this is the vertex set, can you write down this as v1 union v2? So we have seen that x is different from 0, means all the entries of x are different from 0. Okay, that we have seen all the x's are different from 0. Yeah, here we have noted that all the entries of xi are different from 0. So hence, every vertex of the graph G will be part of either v1 or v2. Okay, v1 union v2. And what about the intersection? v1 intersection v2 is empty, because a vertex xi cannot be both positive and negative. Okay, so I cannot be part of both the things. Okay, and indeed, whenever I take an edge from the graph, one end is going to be in v1, the other end is going to be in v2. That's how we are defining this v1 and v2. Okay, so this implies G is a bipartite. Okay, so this says that using Ferrand-Frobenius theorem, if you have a connected graph, then for the connected graph, you don't need the spectral symmetry for the entire spectrum. Only for the largest eigenvalue, if you have, that is good enough. Okay, but eventually, like once you prove this, then bipartiteness will imply the entire spectrum is symmetric. Okay. Okay, I think there are some people who are working in spectral graph theory are attending this seminar series, this lecture series. This quantity is lambda 1 plus lambda n. Okay, so if it is equal to 0, then by this theorem for the connected graphs, you are able to show that then G is bipartite. Okay, G1 equal to minus Gn, sorry, lambda 1 is equal to minus lambda n, that I'm just rewriting. Lambda 1 plus lambda n is equal to 0. Okay, this implies G is bipartite. There is an interesting study people have studied. If lambda 1 plus lambda n is different from 0, okay, can you say G is close to bipartite? Something like you remove some number of vertices or some number of edges, that is going to give you a bipartite graph. Okay? G is some kind of close to bipartite. So if you're interested, you can study. You can search for this literature, or you can just mail me. I can give you some of the papers related to this. Okay. Is the idea clear? When lambda 1 plus lambda n equal to 0, then I'm getting the graph to be a bipartite graph. Okay. Suppose if it is different from 0, suppose it is very close to 0, okay, then it is natural to ask whether that is going to give you some sort of measure of bipartiteness. Okay. So indeed, that is kind of that study has been already done. Okay. Many people studied this notion. Okay. So if you're interested, you can mail me. I'm happy to share the literature. Okay. So, are you with me so far?
Yes, sir.
Okay. So, the next thing is the Coran-Fisher theorem. Okay. So I'm not going to give a proof now. First, I'll tell you the applications of this Coran-Fisher theorem, and then next I will state the interlacing theorems. Okay. First, we will see the applications of these things in the spectral graph theory. Then I will give a proof of these things. Okay. Either towards the end of this lecture or in the next lecture, I will give the proof. Okay. So this says that I think yesterday also we seen this. If A is a symmetric n by n symmetric matrix, and if the eigenvalues are arranged in the reverse way, okay, we were seeing so far lambda 1 is the largest eigenvalue. Only for Coran-Fisher theorem and interlacing, I just got the notation. Okay, maybe I'll fix it in the future. So lambda 1 to lambda n are the eigenvalues. Lambda 1 is the least eigenvalue. Lambda n is the largest eigenvalue. Okay, with the corresponding orthonormal basis of eigenvectors u1 to u1, u2 to un. Okay. If Vk denotes the set of all k-dimensional subspaces of Rn, okay, then we have a nice formula for the kth eigenvalue. Okay, so lambda k is given by you take the Rayleigh quotient x transpose ax divided by x transpose x. Okay, just to maximize it over the k-dimensional subspace. Okay, corresponding to every k-dimensional subspace, you just maximize this Rayleigh quotient first. Okay, and then take the minimum over all possible k-dimensional subspaces. Okay, so this is again an application of spectral theorem. Just you apply the spectral decomposition of A. A is a symmetric matrix. Use the spectral decomposition, and the essential calculations yesterday I have done. Okay, so only we have to do a small trick. Okay, so that I will do after seeing these applications of this thing. Okay, so it's also called the min-max theorem or max-min theorem. Okay. And the same lambda k admits max-min formula. That is, you take the quadratic form x transpose ax divided by x transpose x. You first minimize it over subspaces of dimension n minus k plus 1. Okay, and then take the maximum over all those possible subspaces. Okay. Okay, so yesterday we have seen something, right? Lambda 1 for lambda n. Okay, how to get those formulas from here? Lambda 1 is the least eigenvalue here. Okay, so if I have to find out the least eigenvalue lambda 1, then what I have to consider? V1. Okay, V1 is all possible one-dimensional subspaces. Okay, then this is same as minimum over what I will get. So this is same as what I'm saying. This theorem indeed this implies that minimum over x in x, x in Rn. Transpose x transpose x transpose x is different from 0. Corresponding to every non-zero vector, I will get a one-dimensional space spanned by it. Then the same thing I can write down in this way. What about the max? What about the max version? Oh, I'm sorry. Wait. What I'm doing? Yeah, right. Not lambda 1. Again, lambda 1 here. So what will happen here?
You need to take max size.
No, for lambda 1 only. Just you have to see this. What is happening to V n minus k plus 1.
Only n.
Yes, only one, the whole space you will get, so that maximum will disappear. Okay, very good. Who is that? Yeah, nice. That's what I expect. So if you see for lambda 1, that maximum it's going to be the whole space itself. So that maximum I can discard only the minimum over the one-dimensional subspaces I'm going to get. That's all. Okay. Okay. So here also I'm going to get this. So just to convince yourself, like what we did yesterday, that is kind of particular case of this Courant-Fisher theorem. Similarly, for lambda n also you can see. Okay. In the lambda n, if you see the first case, I think first case this minimum will become vacuous. Okay, we have to take only the over the whole space, that will vanish. Okay. So the proof, rigorous proof, I will give after some time. Okay. Okay. So interlacing theorems. So these theorems are found a number of applications in spectral graph theory. Okay. So today you will see a couple of applications. So the setup is this: if A is a symmetric matrix, okay, and B is a principal submatrix of size n minus 1 by n minus 1. Okay. So without loss of generality, maybe I'm taking B in the first block, something like y transpose some number C. Okay. So B is a n minus 1 by n minus 1 principal submatrix. Okay. If lambda 1, lambda 2 up to lambda n are the eigenvalues of A, and the mu 1, mu 2 up to mu n minus 1 are the eigenvalues of B, then the eigenvalues of A and B, they are nicely interlaced in this way. Okay. The lambda 1, lambda 2, lambda n are the eigenvalues of A, mu 1, mu 2, mu n, they are the eigenvalues of B. Okay. So the smallest eigenvalue of B lies in between the smallest eigenvalue of A and the second smallest eigenvalue of A. Okay. And the second smallest eigenvalue of B lies in between the second smallest eigenvalue of A and the third smallest eigenvalue of A. Here lambda 3 and so on. Okay. So precisely the least eigenvalue of B is greater than or equal to the least eigenvalue of A, and the largest eigenvalue of B is less than or equal to the largest eigenvalue of A. Okay, this is known as the this is one particular case of interlacing theorem. Okay, so one question here arises that okay, A is symmetric, I know, so all the eigenvalues of A are real, but B is a principal submatrix. So B should be also symmetric. As a principal submatrix, it should be a symmetric matrix. Hence, all the eigenvalues of B should be also real. Okay. Hence, the whatever inequalities I'm writing, that they make sense. Okay. Now, there is a general version of this. This is called the Poincare inequality, or Poincare separation theorem, or Cauchy's interlacing theorem, Strum's separation theorem. Okay. There are many names for this theorem. Okay. So this says that. So instead of taking n minus 1 by n minus 1 principal submatrix, you take any principal submatrix. Okay, you take any principal submatrix of A. Okay, so without loss of generality, I'm taking B to be in this corner. Okay, B is an principal submatrix or square submatrix of order n. Okay, so if B is a square submatrix of order m, then that forces that D should be a square submatrix of order n minus m. Okay, so it is easy to see that B is also a symmetric matrix. So let us give name for the eigenvalues. Okay, so let us take A1, lambda 1, lambda 2 up to lambda n be the eigenvalues of the whole matrix A, and mu 1 to mu 2 up to mu m are the eigenvalues of this matrix B. Then we have a general interlacing property for them. So lambda I is less than or equal to mu I, which is less than or equal to lambda n minus m plus I. Okay. So this is not hard to see. So this I can write down n minus m. Oops. N minus m into I. The reason to put a bracket over there is if you take m to be n minus 1, then you are going to get the previous result. Okay. If m is equal to n minus 1, then you are going to get the previous result. So this is a proper generalization of the previous result which we have seen over here. Okay. So what does it say? So the largest the least eigenvalue, okay, of mu of B mu1, okay, that is larger than the least eigenvalue of the matrix A, okay, and this is bounded above by lambda n minus m plus 1. Unlike in the previous case, it sits in between the smallest and the second smallest. Here it sits in between the smallest and the n minus m plus 1 smallest, okay, and so on. If you want to get a bound for the mth eigenvalue of B, so this is less than or equal to lambda n minus m plus m, okay. So that is same as the largest eigenvalue of the matrix B is less than or equal to the largest eigenvalue of the matrix A, and this should be greater than or equal to lambda I equal to m lambda n. Okay, this is not lambda n minus 1, lambda n. Okay, so we will use this result in some of our results. Okay, so I will give a proof of this. Okay, maybe in this lecture or in my last lecture I will give a proof of this. Okay, so is the statements are clear?
Yes, sir. I have one question, sir.
Yes, yes, yes.
So here D have no contribution, means eigenvalue about D is not discussed.
So in terms of D also you can give a bounds, right? So just you arrange what are the eigenvalues, like you take gamma 1 to gamma n minus m. Okay,
Yeah.
for them also you can give bounds like this.
Okay, okay, sir.
Okay.
Yes.
Yeah. Good. Okay, so now let us start proving some of the spectral graph theoretic results. Okay, so Wilf's theorem. So we whatever theorem is written in this slide, that is Wilf's theorem. So the lemmas are the supporting results, which will this is the Wilf's result. Okay, so this says that chromatic number of the graph, you see, the chromatic number should be less than or equal to 1 plus the largest eigenvalue of G. Okay. So lambda max and lambda min, they stands for the largest eigenvalue and the smallest eigenvalues of the corresponding graphs. Okay. Only adjacency. So far I'm discussing with only adjacency. Okay. So the main theorem is this one. So the chromatic number of the graph, I think chromatic number everybody knows. The chromatic number is the minimum number of colors required to color the vertices of the graph such that no two adjacent vertices receive same color. Okay, so whenever there is an edge between two vertices, you should give different color. Okay, so in this way you have to color the vertices of the graph. Okay, and your objective is you need to find the minimum number of colors. Okay, so that chi of G is not an easy quantity to calculate. This is an NP complete quantity, you can't calculate easily. So here this theorem Wilf's result shows that we have a spectral bound for the chromatic number. Okay, so those who have done a course in graph theory, this quantity should remind you something. Have you seen this type of bound for chromatic number somewhere? We got with the lambda max with some other quantity. In terms of vertex degree, do you have any bound for the chromatic number? No? Have you seen this type of result? Chromatic number of G is less than or equal to 1 plus the largest degree of G. What's the name for this theorem? Have you seen this type of result? In such, yeah. You're saying something I'm unable to hear. Maybe you can type also. Hello? Okay, so this is a known result in graph in a first course in graph theory. Brooks theorem, correct? Yeah, this is known as the Brooks theorem, I think. Okay, but I think this inequality chi of G is less than or equal to In fact, the largest eigenvalue of G, except for I think some couple of graphs. I don't remember, maybe triangle and other things. Okay, but anyway, this theorem, Wolff's theorem, can be thought of as weaker version of Brooks theorem. The reason is I'm going to prove that this lambda max is always less than or equal to the largest vertex degree of the graph. Okay, if you use or if you take this lemma 2 for granted, with this lemma for granted, then this theorem, Wolff's theorem, implies the Brooks theorem. Okay, it's not exactly the full version of Brooks theorem. This is part of Brooks theorem. Okay, so let us see proof of the fact one by one. The first thing is, if G is a graph on n vertices and H is a subgraph, okay, not only just subgraph. I guess this should be, maybe let me be on the safer side, induced subgraph. Okay, so whenever you have two vertices in the graph H, if there is an edge in G, then that edge should be there in H also. Okay, then this should happen. This should hold true. Okay, how to prove this? Now translate this problem in terms of the matrices. That's all. So G is a graph. A of G is the adjacency matrix. Okay, so H is a spanning subgraph, not spanning subgraph, induced subgraph on, let's say, P vertices. Then this has an adjacency matrix, A of H. This is an n by n matrix. This is an P by P matrix. Okay. Then what is the connection between A of H and A of G? First of all, it's a submatrix, right?
A principal submatrix.
It is a principal submatrix. Okay. So now let us go back to this thing. So whenever you have this result only. Okay. So here I have B in this block. Okay. So I can think of B as a principal submatrix, or even if B is not in the right block, in this corner block, if it is scattered in this matrix as a principal submatrix, then I can suitably apply the permutation matrices back and forth, and I can bring that B to the corner. Okay, the permutation, pre-multiplying and post-multiplying the permutations like PP transpose will not change the spectrum. So still I have the result for it. Okay, so P by P matrix, this is a principal submatrix. Okay. Now the thing is, now I can apply the this Poincare result here. Okay. So this implies the maximum eigenvalue of the graph G. Okay, this should be at least the maximum eigenvalue of the graph H, and the minimum eigenvalue of G should be at most the minimum eigenvalue of H. This is simply this Poincare. Okay, so now you can see why I need a induced subgraph. If it is not an induced subgraph, then I will not get that as a principal submatrix. Okay, so only for induced subgraph this result holds true. See, I have a graph, I have a subgraph. Okay, induced subgraph. Now the question is, can you compare the eigenvalues of G and H? Okay, so from the Poincare interlacing theorem, from Poincare separation theorem, we can say that the maximum eigenvalue of lambda, okay, so the maximum eigenvalue of G is at least maximum eigenvalue of H, and the minimum eigenvalue of G is at most minimum eigenvalue of H. That's from the Poincare. Okay, I think there is a not typo, that I think max should be in the bottom and G should be in the top. I'll change it when I'm circulating. Okay. Is this proof clear?
Yes, sir.
No. The next thing is, so let capital delta of G denote the maximum vertex degree and the small delta of G denote the minimum vertex degree. Okay. So now I want to show that This capital delta and small delta gives me bounds for the spectral, the maximum eigenvalue of G. Okay. So delta of G, this is the smallest vertex degree, smallest degree. This is less than or equal to lambda max of G. This is less than or equal to capital delta of G. The statement clear?
Yes, sir.
Okay. So let us do this. So let us take the eigenvector corresponding to the eigenvalue lambda max. Okay. So left hand side, let me look at the ith coordinate. Okay. So how to see the ith coordinate? Take the ith row and multiply with the vector x. Okay. So in other words, aij into xj, j equal to 1 to n. This is equal to lambda max of xi. This holds true for every I varies from 1 to n. Okay. Now, this xi should be different from 0. Okay. So maybe if needed, I will just assume, I can assume the graph is connected. Okay. Or even without connectedness also I can do. Okay. So let xk greater than 0 be the maximum coordinate. Okay. I'm doing it without loss of generality here. If minus xk is the okay, so since this is a eigenvector corresponding to the largest eigenvalue, this should be non-negative. Okay, this is fine. Xk is strictly greater than 0, be the maximum coordinate. Okay, just I want to ensure that I have a non-zero coordinate. Okay, so this gives me lambda 1 into xk. This is equal to lambda max. Okay, lambda max into xk. This is equal to summation j equal to 1 to n akj into xj. Okay. Now, this quantity is less than or equal to xk is the maximum, so I can take xk outside. Okay, into summation j equal to 1 to n akj. What is this quantity? This is the kth row sum. Okay, so kth row sum gives the degree of the vertex k, and this quantity is of course less than or equal to the maximum vertex degree of your graph G. Okay, so this gives degree of the vertex k, a degree of the vertex vk. Okay, that is less than or equal to the largest degree. Okay, so now xk I have chosen it to be the positive coordinate. This implies lambda max should be less than or equal to delta of g. Just by simply expanding this eigen equation, you get this inequality, first inequality. Okay, so I didn't use any tool, just to use the matrix vector multiplication and then applied the taking maximum outside. Okay, so now I had to prove that the bottom inequality, delta of g is less than or equal to lambda max. So this one we have almost seen the proof yesterday. Okay, so lambda max is equal to maximum over x different from 0 x transpose x divided by x transpose x. Okay, so to get some bounds for this lambda max, okay, you can choose some particular vectors and try to get bound for it. This idea yesterday we have seen. So you can choose your vector x to be all ones vector. Okay, So this implies lambda max is greater than or equal to 2m by n. Right? Yesterday we have seen this. Because E transpose AE just sums all the entries in the matrix A. That is like twice the number of edges. Okay. And then X transpose X is like that is just n. Now, you see 2m. 2m is nothing but sum of the degrees of the vertices. Okay. So if you call VIs, if you take the sum of the degrees of the vertices, then you get twice the number of edges. Okay. Now you can complete the proof. Okay. This quantity is greater than or equal to, you take the minimum vertex degree out, and then everywhere you get delta plus delta plus delta up to n times. Okay. So this implies lambda max is greater than or equal to, in place of 2m, I can replace with delta n, delta times n divided by n. This is delta. Okay. So that is together what we have obtained. Lambda max is less than or equal to delta, and this is less than or equal to the small delta. Just you are applying the variational characteristic. Okay. So now let us see a proof of Wilf's theorem. Okay. Oops. Okay, I may need it there. Now proof of Wilf's theorem. So we'll prove it using induction. Okay. First we will avoid the trivial cases. Okay. So if chromatic number of G is equal to 1, will be write down the statement for ready reference. What is the groups? What is the Wilf's theorem? Chromatic number of G is less than or equal to 1 plus the lambda max of G. Lambda 1 I might have written there. That is okay, lambda max. I have written lambda max. Okay, lambda max of G. Okay. If lambda 1 of G, sorry, chi of G is equal to 1, then what do you know about the graph? The chromatic number of the graph is equal to 1 only when the chromatic number is equal to 1. The graph does not have any edges. Okay. So in that case, minimum vertex degree I can directly say lambda max of G is equal to 0. So that is chromatic number of G is less than or equal to 1 plus lambda max of G. Okay. If chromatic number is equal to 1, then you don't have any edge in the graph. Okay, that means the graph is an empty graph, null graph. Empty graph, there is no edges in the graph. That means that the adjacency matrix is 0 matrix and 0 is the eigenvalue. Okay. Now, what about the other cases? Let us prove one by one. Okay. So let us take a chromatic number of G is equal to P with P greater than or equal to 2. Okay. Now from this G, let me extract a induced subgraph in this way. Kind of critical graph. Okay. So what is that? Let H be a subgraph. Sorry. Let H be a subgraph of G such that chromatic number of H is equal to P. Okay. And if you remove any vertex from your graph H, okay, this should have chromatic number strictly less than P. Okay. So chromatic number of G is equal to P. So I'm trying to extract a subgraph H from G such that chromatic number of H is equal to P and the chromatic number of H minus any of the vertices it's strictly less than P. Okay. So by a greedy type of thing or by brute force you can get it. Okay. Now what I'm claiming, the least eigen the least vertex degree of H should be at least P minus 1. Okay. So this is easy to see in a way. The reason is if suppose that the least vertex degree of H is strictly less than P minus 1. Okay. Then what can I do? So there is a vertex which is having vertex degree strictly less than P minus 1. Just remove that vertex. Okay. After removing that vertex, okay, so I will be able to color the graph using less than or equal to P minus 1 colors. Okay. That's how we have chosen our H. So we let degree of some Vi be strictly less than P minus 1. We have a chromatic number of H minus Vi. Okay. This quantity is strictly less than P. Okay. That means that H minus Vi can be colored with at most P minus 1 colors. Okay. Now if you again join this vertex Vi to H, okay, then the vertex Vi can be colored with one of the P minus 1 colors. One of the P minus 1 colors in H. Okay. H minus Vi we are able to color using P minus 1 color, at most to P minus 1 colors. Okay. And the degree of Vi is strictly less than P minus 1. That means that the neighbors it has at most P minus 2 neighbors. Okay. In the worst case, if it has P minus 2 neighbors, you might have used P minus 2 colors. Still, you will have one color left. That color you can use it for the vertex V. That means that H is P minus 1 colorable, which is not true because we have taken chromatic number of H is equal to P. Right? Chromatic number of H is equal to P, so you can't do that. Okay, so that means that the minimum vertex degree of the graph H should be greater than or equal to P minus 1. Okay. Now, lambda 1 of H, this is greater than or equal to the minimum vertex degree of H. Lambda 1, I'm sorry, I will lambda min. Okay, sorry, lambda max. The maximum eigenvalue of H is greater than or equal to the minimum vertex degree, right? And this is greater than or equal to P minus 1. Now, previously, we have seen that the maximum eigenvalue of G is greater than or equal to the maximum eigenvalue of H for any of its principal for any of its subgraphs, induced subgraphs. So this implies that P less than or equal to 1 plus lambda max of G. What is P? P is nothing but the chromatic moment. This is what I want to show. So I'll show you the proof again. So we have to show that this chromatic number of G is less than or equal to the 1 plus the maximum eigenvalue of G. Okay. So the proof is like this. First take the chromatic number is equal to 1. Chromatic number is equal to 1 is the trivial case. Okay. So in which your graph does not have any edges, you can conclude easily. Okay. So now it's not even induction. Okay. So chromatic number of G is equal to P. You take any graph with the chromatic number is equal to P. I'm going to prove that for this graph, you are going to get the Wills inequality. Okay. So in order to do that, first extract a subgraph H of G such that H is having this property. Chromatic number of H is equal to P, and you remove any of the vertex from the graph H, you're going to get the chromatic number of the resultant graph is strictly less than P. Okay. So now I claim that in this graph, okay, in this H, the least eigenvalue should be greater than or equal to P minus 1. Okay. So in order to get this identity or this inequality, you need this minimality with respect to this chromatic number. Okay, that's a crucial step. So that can be easily done. That is kind of again greedy thing. If you can, if the minimum vertex degree is less than or equal to less than P minus 1, that is less than or equal to P minus 2, then H minus VA, that is already P minus 1 colorable by the way we constructed H. Okay, and VA is the vertex of degree at most to P minus 2. Hence, you can use some of the colors which you used for H minus VA. Okay, so that's going to give me a P minus 1 coloring for H itself. That is not possible. Hence, the inequality delta of H is greater than or equal to P minus 1 holds true. Okay. So now delta of H is greater than or equal to P minus 1, and for H, if you apply this, lambda max is greater than or equal to delta of H. So I'm getting this part. Okay. So lambda max of H is greater than or equal to delta of H. This I have proved in the lemma. And lambda max of G is greater than or equal to lambda max of H, again using the variational characterization we have shown, or interlacing. This is exactly interlacing. Okay. So this completes the proof of Wills theorem. Okay. So do you have any question?
When the equality will hold other than complete graphs?
For the complete graph, whether do we get any equality? Yeah, I think if you take odd cycle, what is happening for odd cycles?
Yes, it will be 3 less or equal to 1 plus, I think spectral rate, maximum eigenvalue is 2, right?
Yeah, so I'm not sure. For complete graph, I think for odd cycles it may be true. Like the Brooks theorem, which says that lambda of G is chromatic number is less than or equal to delta of G for all other graphs. I'm not sure whether that is true here also. I have to check that.
Okay.
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 So lambda max for complete graph is n minus 1. Chromatic number is n. Yeah, for complete graph it is true. For odd cycle also you see. Okay. So cycles itself is true, right? Why I need odd cycle? For even cycle also. For even cycle, what is the okay, sorry. Even cycle 2 is the eigenvalue, but chromatic number is 2. But for even cycle, chromatic number is 3. Sorry, for the odd cycle, chromatic number is 3. Okay? Yeah, for odd cycles, for complete graph, you can see from here equality holds. Okay, but unlike the classical what is that? Brooks theorem. So I don't know whether this is chi of G is less than or equal to lambda max of G for all other graphs. It's a good question to think. Okay, so next I want to show you a proof of Hoffman theorem. Okay, so yeah, this proof is really simple, but we have split the proof into various steps. Okay, so I can quickly go through the proof. Okay, so if B and C are symmetric matrices, then the maximum eigenvalue of the matrix B plus C is less than or equal to the maximum eigenvalue of B plus maximum eigenvalue of C. Okay. So this proof is not hard to see. So B and C are symmetric matrices. So B plus C is a symmetric matrix. So I can use the variational characterization. Okay. And in fact, I don't want to use that I want to use the special version, okay, which you can take that as an exercise. So instead of dividing by 2 norm, instead of dividing this by this X transpose X, you can restrict yourself to only the norm 1 vectors. Okay. So from whatever we have proved as a variational characterization, from that we can easily get this. Okay, just you can take that as an exercise. Now from here, so this is same as maximum over X transpose Bx plus X transpose Cx, such that 2 norm of this is equal to 1, and this is just less than or equal to maximum over X transpose Bx, such that this 2 norm is equal to 1 plus maximum over X transpose Cx with not equal to. What about these two quantities? They are nothing but lambda max of B plus lambda max of C. Okay, just simply by the variational characterization, we are able to prove this inequality. Okay. Now the next thing is for positive semi-definite matrices. Okay, so the first result is true for arbitrary symmetric matrices, but the second result is true only for positive semi-definite matrices. Easily construct counterexamples for non-positive semi-definite matrices. This result need not be true. Okay, the result says that if you have a 2 by 2 block matrix, B equal to B11, B12, B21, B22. Okay, then the maximum eigenvalue of the matrix B is less than or equal to the maximum eigenvalues of the blocks. You take this sum. Okay, sum of the maximum eigenvalues of the blocks. Okay, the statement clear what you are doing? So this proof is really nice. So B is PSD. Okay, and B is given in the form B11, B12, B21, B22. So yesterday we have shown that if B is a positive semi-definite matrix, then I can find out a matrix C such that B can be written as CC transpose. Okay. So now let me partition C into 2 by 1 blocks in this C1, C2, such that the partition is conformal with the partition of B. Okay. What do I mean by that? That is, if I take a CC transpose, that is C1, C1 transpose, C1, C2 transpose, C2, C1 transpose, C2, C2 transpose. This is equal to the block matrices B1, B12, B21, B22. Okay. So this is an 2 by 1 matrix, and C transpose is a 1 by 2 block matrix. The resultant will be a 2 by 2 block matrix. Okay. So this implies, so B11 is equal to C1, C1 transpose, B22 is equal to C2, C2 transpose. Now let me calculate lambda max of B. Okay, lambda max of B is same as lambda max of CC transpose, and this is same as, this is a result in linear algebra, C transpose C. When you take the product AB, BA, if AB, BA both the matrix multiplications are defined and if they are square matrices, okay, then the spectrum will be same up to the 0 eigenvalue. Okay, except the change can be there only in the 0 eigenvalue. Okay? So lambda max will not change. Okay, and what is C transpose C? So C transpose C is C1 transpose C1 plus C2 transpose C2. Okay, so why it is the case? So C is given by C1 C2. Okay, so C transpose is given by C1 transpose C2 transpose. Okay, so CC transpose will be C transpose C will give me C1 transpose C2 transpose C1 C2. Okay, just you are going to get this. Now I have two symmetric matrices. Just in the previous slide, I have shown that I can take the maximum for each of the terms. Equality will become inequality. Okay. And this is same as C1 transpose C1, the lambda max is same as the maximum of C1 transpose plus the lambda max of C2 transpose. Now, what is lambda max of C1 transpose? So C1 transpose is same as B11, C2 transpose is same as B22. That is same as lambda max of B11 plus lambda max of B22. That is what I want to show. Okay. Just purely manipulation. Okay. Use this the Kolesky decomposition of the positive semi-definite matrix, and then have to use the whatever tools we have developed so far cleverly. Okay. Now, using this, we can prove this for the following results. Okay. So, if B is a n by n symmetric matrix, okay, and if we can partition B in this way, okay, B1, B2, B11, B12, B21, B22, and so on, where this B11 is a square matrix, okay, then the maximum eigenvalue of B plus the minimum eigenvalue of B, okay, it should be less than or equal to the maximum eigenvalue of B11 plus maximum eigenvalue of B22. Okay. So in the previous slide, if you see, so I'm able to show that the maximum of for positive semi-definite matrices, the maximum of B is less than or equal to maximum of B11, maximum of B22. Now I don't want this positive semi-definiteness. I want to see what will happen for the just a symmetric matrix. Okay. So the payoff is not just only lambda max, just add lambda min with lambda max. Okay. If it is a positive semi-definite matrix, then lambda min of B equal to 0. So you are going to get back to your original result, what we proved. Okay. So this is a standard technique in matrix theory. When you know something for positive definite matrices, you want to prove something for the symmetric matrix, then how to construct a positive semi-definite matrix from a symmetric matrix. Okay. So one way is look at the least eigenvalue of the symmetric matrix, okay, and then subtract so the least eigenvalue times identity from the given matrix. You are going to get a positive semi-definite matrix. Okay. So the next proof is I want to prove this. Okay. So B is symmetric. Okay. B is symmetric. So this implies if I take B minus lambda min, okay, lambda min of B minus I, this is a positive semi-definite matrix. Why it is the case? So B minus lambda min of B times identity is a symmetric matrix. There is no doubt about it. And from all the eigenvalues, you are subtracting lambda min. Okay. So it looks like you are subtracting, but we are adding the negative of lambda min. That means that all the eigenvalues will get shifted by lambda min. Okay. So lambda min is the least eigenvalue for B. So now that will become 0. That will correspond to 0 eigenvalue for this new matrix B minus lambda min. So rest of the eigenvalues will be non-negative. Symmetric matrix with non-negative eigenvalues. So that will be a positive semi-definite matrix. Okay. So let us see in terms of block matrix, how does it look like? So this is B11 minus lambda min of B times identity B12, B21, B22 minus lambda min of B times identity. Okay. So this is a positive semi-definite matrix. Okay. So now I can apply the previous lemma. The previous lemma says that lambda max of B is less than or equal to lambda max of so this is not just B, right? B minus lambda min of B minus identity. Okay. So now here this is not just B, this is B minus lambda min of B identity. Okay, this is lambda max of the diagonals B11 minus lambda min of B identity plus lambda max of the other diagonal, that is B22 minus lambda min of B. Okay. Now again, like you have a matrix and you are subtracting or adding a multiple of identity, that is going to just shift the spectrum. So this will imply, so lambda max of B plus lambda min of B times identity. Okay. So here I have a minus. Okay. In the left hand side I have a minus, but in the right hand side I will get 2 times lambda min of B. Okay, here I have a minus lambda min of B. The left hand side I have 2 times minus lambda min of B. I can bring that to the left hand side, that I'm going to get the required result. This is less than or equal to lambda max of B11 plus lambda max of B2. This gives the proof of the first thing. Okay, done with this proof. Okay, so see this proof. If you have any doubt, we can discuss this. Do you have doubt?
Sir, this step B is symmetric implies B minus lambda min of B times I is PSD. So there, this right hand side matrix is PSD because lambda min is the minimum eigenvalue of B, right? Okay.
Yes. We are shifting all the eigenvalues by lambda min.
Okay, got it.
Okay. So our ultimate aim is to prove the Hoffman's bound. Okay. So if you are done with all these intermediate lemmas, like Hoffman's lemma is just a we can derive in a single step from yeah, almost we are done with the proof of Hoffman's theorem. Okay. Let's do, okay, I don't want here. Okay. So next let us prove this. So you take a let's say K by K partition matrix of this form. Okay. So K by K matrix, all whose diagonal blocks are 0 blocks. Okay. So we have rest of the blocks are given by some Bij's. Okay. Now this lambda max of B plus K minus 1 times lambda min of B. Okay. This quantity is less than or equal to 0. Okay. So for 2 by 2 block, what is happening? When you take K equal to 2, for K equal to 2, what are you getting? So this is same as lambda max of B plus K minus 1, that is 1 into lambda min of B. Lambda max of B plus lambda min of B is less than or equal to 0. That follows from the previous lemma. Right? The diagonals I'm keeping 0. Lambda max of B plus lambda min of B is less than or equal to lambda max of the diagonals. Diagonals are 0, hence I'm getting K equal to 2, and this follows from the previous thing. Okay, follows from the previous one. Follows from this one. Okay, so now I'm going to give induction proof. Okay, so how to do that? So K equal to 2 we are already done. Assume the result holds true for Okay, this is the proof for the fact that lambda max plus k minus 1 into lambda min is less than or equal to 0. Okay, assume that the result holds true for k minus 1. Okay, k minus 1, block matrix of size k minus 1. Okay, so let us take C to be a principal submatrix of C, a principal submatrix obtained by deleting some block row and the same block column. Okay, block obtained by deleting principal submatrix of B obtained by deleting. To be precise, let us take the last row and last column. Last column blocks of B. Okay. Then for this C, we can apply the induction hypothesis. Okay, that is C is a k minus 1 by k minus 1 block matrix. Therefore, lambda max of C plus k minus 1 into lambda min of C is less than or equal to 0 by induction. Okay, so now by the previous lemma, we have this lambda max of B plus lambda min of B is less than or equal to lambda max of C. Okay, the reason is B, I am thinking of block matrix of this form. C is here, 0 is here. So here, whatever left out from the first row, or the rows corresponding to C, the columns corresponding to C. Okay, so now this is a new block matrix. B is of the form C. Okay, the k minus 1 by k minus 1 principal submatrix, I'm keeping it in a single block. Okay, for that I'm applying the previous lemma. So that gives me this inequality. Okay. See, also lambda min of B is less than or equal to lambda min of C. Okay, the minimum eigenvalue of B is less than or equal to minimum eigenvalue of C because that is by the interleaving. Okay, so therefore, combining all these facts, I'm going to get lambda max of B plus lambda min of B. Okay, this which is less than or equal to lambda max of C, which is less than or equal to so here lambda max is less than or equal to k minus 1 into minimum of this thing, right? So minus k minus 1 of lambda min of C. K minus 2, I'm sorry, here it is, I'm applying for k minus 2, right? This is k minus 2 of C. So this implies, so here also you see, okay, so I will get it here. Okay, so this is less than or equal to lambda max of, this is indeed equal to lambda max of B plus lambda min of B. And the lambda min of B is already less than, so here I will get k minus 2 into lambda min of B. This is less than or equal to 0. Okay. So this together will imply lambda max of B plus k minus 1 into lambda min of B is less than or equal to 0. This is what I want. Okay, so once this result is clear, we can directly give a proof of Hoffman's bound. Okay, so I don't even need a new thing. So if the chromatic number of G, let us say it is equal to K, then you can partition the vertex set into K parts. V1 union V2 up to union Vk. Okay, so Vi's are the color classes. That means that between the vertices of Vi's or V1 to itself, I don't have any edge. V2 to itself, I don't have any edge. So if you use the Vi's for the labeling of the vertices, okay, this I mean V1, V2, and so on. If you write like this up to Vk, V1, V2 up to Vk, here all the diagonals are equal to 0. Now I can apply this result, what we have shown. Okay, lambda max of B plus k minus 1 into lambda min of B is less than or equal to 0. That is lambda max of our G plus k minus 1 times lambda min of G is less than or equal to 0. This is same as saying that k is greater than or equal to 1 minus lambda max of G divided by lambda min of G. Okay, first take the max other side. Okay, lambda min of G is always negative. Okay, maybe precise, to be precise, G is not an empty graph. G has at least one edge. Otherwise, you may face some problem. G has at least one edge. Okay, so that lambda min I can divide. It is a negative quantity that will reverse the inequality. Then you bring the one other side. That's all. Okay. Okay. So this is all about the Hoffman's bond. So I think most of the topic what I have to cover, I have covered. In the last lecture, I will do something related to the Savitkowicz inertia bound and then hypergraphs. Something related to sensitivity conjecture. I will talk. Okay. Okay, for all this part, the standard reference is book by Bappert. Okay, Graphs and Matrices by Professor Bappert, and then Spectra of Graphs by Brower and Amos, and then Introduction to Theory of Graphs by Savitkowicz and Rawlinson Smith. Okay, so you can see all these results. Most of the results you can find in Professor Bappert. Okay, do you have any question? Okay, I'll stop recording. Yes. Yeah. What's the question?
In the last one, we have, can you, and that lambda min of G, we just make sure that it is non-zero, and that's why we are taking that G as at least one.
Yes. Lambda max is different from 0 because the graph has at least one edge. So I can divide it by lambda min. Clear?
I'm talking about lambda min of G. We have to show that, I mean, make sure that it is non-zero.
Your voice is not audible. What are you saying? Why lambda min is different from 0? Is it your question?
Yeah.
Because if your graph has at least one edge, then it's a symmetric matrix. The adjacency matrix is a symmetric matrix with at least one non-zero entry. When you have at least one non-zero entry, then the largest eigenvalue should be positive and the least eigenvalue should be negative. Then again, you can use the interlacing, right? If X is a symmetric matrix, if A is a symmetric matrix, if it has a non-zero entry, let's say in some ijth place, then jith place also should be non-zero. Okay. Now look at the principal submatrix, 2 by 2 principal submatrix corresponding to this ij and jth entry. So ith row, jth row, ith column, jth column. So for that matrix, we have positive eigenvalue and negative eigenvalue. Okay. Hence, that is going to tell you that by interlacing, the largest eigenvalue of A should be positive, and the least eigenvalue of B should be least eigenvalue of A should be negative.
Okay, sir. Thank you.
Yes. Yeah. Other question? Okay. If not, I will stop recording here.